Your body would be ash long before the sun ever reaches you. But let's begin gently. From far away, picture yourself drifting at the edge of the solar system, farther out than any planet, looking back toward a small yellow point of light. That point is our sun. From here it looks calm, steady, almost small enough to hold in your hand. This is how the sun has looked for billions of years, and how it looks tonight as you settle in and let your eyes close. The sun is a star, one of perhaps 200 billion in our galaxy alone. It is not especially large. It is not especially bright. In the great quiet count of stars, it is ordinary, and yet everything you have ever known depends on it. The warmth on your skin on a summer day, the green of every leaf, the rhythm of night and day, all of it traces back to this one modest ball of light, hanging in the dark, holding 8 planets in its gentle pull. Right now, the sun is stable. It burns hydrogen into helium in its core, releasing light and heat in a balance that has held steady for about 4.5 billion years. If you could float close enough to feel its warmth without being harmed, you would feel something like the safety of a low, distant fire. Reliable, unhurried, not something you would think to fear. But stars are not permanent things. They change, they age, and this particular star, our star, carries within it a future that is already written into the physics of how it burns. One small thing before we drift further out. The universe has a new wonder for you every single night here. If you'd like one waiting each evening, subscribe and let it find you. Billions of years from now, this same quiet star will begin to swell, not suddenly, not violently, but slowly over hundreds of millions of years, the way a held breath is finally released. It will grow into what astronomers call a red giant, a late stage of a star's life, when its outer layers expand outward, sometimes by 100 times, sometimes by 200 times its original width. The sun that fits so easily into your palm from out here will become something else entirely, something vast enough to reach past the orbit of Mercury, past Venus, perhaps, though this is still debated, close enough to touch the Earth itself. This is the mystery we will sit with tonight, not because it is frightening, but because it is genuinely unknown in its details. We know, with real confidence, that the sun will expand. This is settled physics, observed in countless other stars across the galaxy that have already lived through this stage. What we do not know, not with certainty, is exactly which of our planets will be consumed by that growing fire, which might somehow drift free of it, and what the last days of a world would actually feel like as its sun grows close enough to fill the entire sky. Some researchers believe Mercury and Venus are almost certainly doomed, drawn inward and vaporized. Others wonder whether Earth might slip outward first, pulled by the sun's own slow loss of mass, escaping the flames by a matter of some fraction of an orbit. The evidence is incomplete, pieced together from models, from mathematics, from the scarred and swollen stars we have found elsewhere in the sky that seem to be living through this very transformation right now, if you lived long enough to see it. And no living thing ever will. You would watch the sun grow larger in the sky, year after year, century after century, not as a sudden blaze, but as a slow, patient swelling, the edge of the star creeping outward the way a shadow lengthens at the end of a long afternoon. There would be no single moment of alarm, only a gradual, almost gentle closing of distance between you and something enormous. Tonight, we will move slowly through this future. We will look at the sun as it is now, the quiet furnace holding everything together, We will watch, in our imagination only, as it begins to change. We will visit each planet in turn, wondering together which will be swallowed, which might escape, and what it would mean to be a small, warm world spiraling ever closer to a star that used to feel so safe. None of this is settled. Much of it remains a question mark, drawn out across billions of years we will never see. For now, you are safe. The sun above you, wherever you are, still burns the way it always has. Let that steadiness hold you as we drift further into the dark to wonder. Close your eyes for a moment and picture a ball of light so wide that 1,000,000 Earths could fit inside it. That ball is the sun. It sits about 93 million miles from where you are lying right now, close enough that its light reaches you in just over 8 minutes, and far enough that its heat arrives gentle instead of searing. You already know its warmth on your skin. What you may not picture as easily is what makes that warmth possible deep inside, where no light has ever escaped to show us directly. At the very center of the sun lies its core, a region so dense and so hot that hydrogen atoms are crushed together until they fuse into helium. This process, called nuclear fusion, releases enormous energy every single second. The core's temperature reaches about 27 million degrees Fahrenheit. If you could somehow stand there, your body would not simply burn. It would be undone at the level of its atoms, faster than thought, faster than pain. The sun has been doing this quietly for about 4.5 billion years. That is longer than there have been mountains on Earth in their current shape, longer than there have been oceans holding the shorelines we would recognize. And yet, in human terms, the sun is only middle-aged. Astronomers place it about halfway through the portion of its life when it burns hydrogen steadily in what is called the main sequence. This is the calm, stable stretch of a star's story, the part where nothing dramatic seems to happen from one century to the next. The sun is made almost entirely of 2 elements. About 3/4 of its mass is hydrogen, the simplest and lightest element there is. Almost all the rest is helium, the product of that constant fusion in the core. Everything else, all the heavier elements that make up planets and oceans and living things, adds up to less than 2% of the sun's total mass. In a very real sense, you are built from the sun's rare leftovers, the small fraction it did not keep for fuel. The energy made in the core does not travel to the surface quickly. It can take hundreds of thousands of years for light to work its way outward through the dense layers surrounding the core, bouncing and scattering the entire way. Only in the outer third of the sun does energy move by convection, where hot material physically rises and cool material sinks, the way soup churns slowly on a stove. By the time that energy finally reaches what we call the surface, the photosphere, it has traveled for an age older than our species, only to escape into space and cross the last 93 million miles to you in minutes. This steady, ancient furnace has kept a nearly constant output for billions of years, which is one reason life on Earth has had time to grow, change, and become complex at all. But steady is not the same as permanent. Every second, the sun converts about 4 million tons of matter into pure energy, and it has been doing that every second for billions of years. Some researchers wonder how long a star can keep this exact balance before something in its structure has to shift. The core cannot hold the same composition forever. Hydrogen is a resource, and even a star this size is slowly using it up. Here is where the open question of this whole story begins to take shape. Stars do not stay the same forever, even ones as steady as ours. The same fusion that has warmed you your entire life is also, very slowly, changing what fuel sits inside the sun's core. Scientists broadly agree on the physics of hydrogen fusion turning to helium, but there is still real debate over the finer details of exactly how a star like ours will respond once that hydrogen supply thins out in the core. Some models suggest a smoother transition. Others predict more turbulent shifts in the sun's inner layers. The overall direction, though, is not seriously contested. A star's fuel supply is finite, and finite things end. If you have ever watched a candle burn low toward its base, you have seen a small, safe echo of what is happening in slow motion at the center of our star. Nothing about this is imminent. Nothing about this should keep you awake with worry tonight. But it is true, and it is strange, and it is worth simply sitting with for a moment. The same sun that has warmed every sunrise you have ever seen is, underneath its calm gold light, a furnace that is quietly rewriting itself. What that rewriting eventually means for the planets orbiting it, including the one beneath you right now, is where our attention turns next. Picture a small kitchen deep inside the sun, so small you could hold it in your two hands and know that every bit of the sun's light comes from that tiny space. This is the core, the heart of the furnace we spoke of a moment ago. Right now in that core, hydrogen is turning into helium, and that quiet trade has been going on for about 4.5 billion years. If you sat there and watched, you would feel the weight of all that time pressing down, patient and unhurried. The sun does not burn like a candle or a campfire. It fuses deep in that hot, crushed core. Hydrogen atoms slam into each other with such force that they join together and become helium, releasing light and heat in the process. This is nuclear fusion, the same basic process that powers every star you have ever seen twinkle in the night sky. It is slow, steady work, and it has kept the sun shining at nearly the same brightness for longer than the Earth has had continents in their current shape. But nothing lasts forever, not even a furnace this steady. The hydrogen in the sun's core is a finite supply, like a bag of flour that gets a little smaller with every loaf of bread. Right now, the sun has used up something close to half of the hydrogen available in its core. Your body, if it could somehow sense the passage of stellar time, would feel this moment as roughly the midpoint of the sun's adult life. Not old, not young either, simply past the middle of something enormous. What happens when the hydrogen in the core starts running low is where the real story of change begins. As hydrogen becomes scarce at the center, the fusion there slows down. Less fusion means less outward pressure, pushing back against gravity. And gravity, patient as always, responds immediately. The core begins to shrink under its own weight, squeezing inward, growing hotter and denser as it does. Here is where one of the strangest ideas in stellar science comes into play, and it is worth sitting with slowly as the core contracts and heats up. A shell of hydrogen surrounding that core starts fusing instead, and it does so with surprising intensity. This shell burning, as scientists call it, actually produces more energy than the core did in its younger years. The outer layers of the sun, responding to this new flood of energy from below, begin to expand outward. The sun does not shrink as its fuel changes. It swells. This is one of the strange truths astronomers have puzzled over for decades. Something as central to the sun as its hydrogen fuel does not run out and go dark. It runs low and forces a kind of internal argument between gravity, which wants to collapse the core, and fusion, which keeps finding new fuel to burn in new places. The result of this argument, played out over hundreds of millions of years, is a star that grows larger even as it seems to be aging. Some researchers describe this as the star reorganizing itself in response to scarcity. Others frame it more as an inevitable mechanical consequence of gravity and pressure, finding a new balance. Both descriptions point to the same slow transformation, even if the language differs. There is still real uncertainty in the exact timeline of this process. Models, built on our understanding of stellar physics, suggest the shift from steady hydrogen burning to shell burning, and the resulting expansion will unfold gradually over roughly 1 billion years, starting a few billion years from now. But models are not the same as observation, and no one has ever watched a star exactly like our Sun move through this transition from beginning to end. Astronomers instead study other stars, ones further along in their own aging, and try to piece together a shared story from many partial glimpses. If you could stand at a safe distance and watch this unfold across those long stretches of time, you would not see anything sudden. There would be no flash, no dramatic signal marking the moment the core began to change. You would only notice, century by century, that the star seemed to be breathing outward, its light reaching slightly farther than it once did. The change is real, but its pace belongs to a clock far slower than any human one. This is the first quiet turn in the Sun's long story, the moment when its fuel begins to change and its shape begins to answer. The core will keep contracting, the shell will keep burning, and somewhere in that gradual shift lies the beginning of an ending that has not happened yet, and one we still do not fully understand in all its detail. Picture the Sun as it is tonight, quiet and steady, its light falling gently across your closed eyelids through some window far away. Deep inside it, something small and patient is beginning to shift. If you could shrink down and drift into that furnace, your body would feel the pressure rise long before the heat became unbearable, layer after layer pressing in as you fell towards the center. The Sun's core is where hydrogen atoms have spent billions of years fusing into helium. This fusion is a joining of small atoms into a bigger one, releasing light and heat in the process. Helium, unlike hydrogen, does not want to fuse at the temperatures found there now. It piles up quietly, ash from a fire that has been burning since before the Earth existed. Some researchers describe this helium ash as an inert core, a term that just means a region no longer producing its own energy. Little by little, that region grows heavier and more crowded. Gravity does not wait for permission. As the ash-heavy core presses in on itself, it contracts, meaning it pulls tighter and smaller under its own weight. You might picture a fist slowly closing around a handful of sand. That closing motion matters more than almost anything else in this story, because it is the switch that will one day turn a calm yellow star into something far larger and far redder. The contraction raises the temperature and pressure in a thin shell of hydrogen wrapped just outside the helium core, and that shell ignites in a hotter, faster kind of fusion than the core ever managed on its own. Here is where the Sun's building blocks start to disagree with each other. The core shrinks, the shell burning around it grows fiercer, and the outer layers of the Sun, the vast quiet gases that make up almost all of its visible bulk, respond by doing the opposite of the core. They expand outward, swelling like dough left too long in a warm room. If you stood at a safe distance and watched this happen over millions of years, you would see the star's surface drift outward, its light dimming in intensity even as its total brightness climbs, because that light is spreading across a much bigger surface. This is one of the stranger truths about a star nearing this stage of its life. A shrinking heart and a swelling body happening at the same time, driven by the same imbalance. Some astronomers frame this as a kind of argument between layers, the dense core pulling itself smaller, while the outer hydrogen and helium gases loosen their grip and drift toward the dark. Others prefer to describe it as a redistribution, energy pouring outward from the hotter shell and pushing the outer material away, like smoke rising from a chimney. Both descriptions point to the same unresolved detail. The exact rhythm of this internal shift, how quickly it accelerates, and what triggers each new phase still depends on models that are refined but not perfectly settled. Every element involved in this slow transformation has a history that reaches far beyond the sun itself. The hydrogen fusing tonight formed in the first minutes after the universe began. The helium collecting in that ash-heavy core also formed then, mixed later with helium made by other, older stars. And the heavier elements scattered faintly through the sun, tiny traces of carbon, oxygen, iron, came from stars that lived and died long before the sun ever gathered itself out of a cloud of gas and dust. In a real sense, the material now quietly rearranging itself inside our star was forged in the depths of stars that vanished ages ago. If you rest your hand against your chest, the iron in your blood shares that same distant origin, cooked inside a star that no longer exists. Nothing about this process happens quickly by human measures. The shift from a stable, hydrogen-burning star to a swelling giant unfolds across hundreds of millions of years, a pace too slow for any single lifetime to notice. Yet, somewhere in that vast stretch of time, the outer layers will begin reaching outward far enough to touch the space where Mercury circles, then Venus, then perhaps Earth itself. The order of events is fairly well agreed upon among researchers who study stellar evolution, though the exact size the sun will reach and exactly which worlds will be swallowed outright remains an open question we will sit with as this night continues. For now, the core simply contracts, the shell simply burns hotter, and the outer layers simply begin, ever so slowly, to answer. Picture two forces locked in a very long argument. One is gravity, pulling every atom in the sun toward the center. The other is pressure, pushing outward from the heat of fusion, the process of small atoms fusing into bigger ones, releasing light and warmth. For most of the sun's life, these two forces have matched each other almost perfectly. If you could stand at a safe distance and watch, the sun would look calm, steady, unchanging year after year. That balance is the only reason a star can shine quietly for billions of years instead of collapsing or exploding. The core is where this argument really happens. It is a ball of plasma squeezed so tightly that hydrogen atoms fuse into helium, releasing the light that eventually reaches your face on a warm afternoon. As the hydrogen runs low, the core cannot make enough outward pressure to hold gravity's pull at bay. So gravity wins just a little. The core shrinks. It packs in tighter, and as it tightens, it grows hotter. This heating is not a small detail. It is the spark that begins the whole transformation into a red giant. Here is where the story turns strange. You might expect a shrinking, heating core to make the whole sun shrink too. Instead, the opposite happens to the outer layers. The extra heat pouring out of the tightening core pushes into the layers of gas above it, and those layers respond by puffing outward. The sun's face, its visible surface, begins to swell. If you were floating nearby to watch this unfold over millions of years, you would see a star that is somehow both collapsing at its heart and expanding at its skin, two motions happening at once, one hidden and one enormous. This is the mechanism behind the phrase red giant, and it is worth sitting with because it is not obvious. Some researchers describe it as a kind of overcorrection. The shrinking core burns hotter than the whole star needs, and that surplus heat has nowhere to go but outward, inflating the sun's outer atmosphere far beyond its current size. Others focus less on the core itself and more on a thin shell of hydrogen fusion that forms just outside it, a bright ring of burning material that becomes, for a time, more influential than the core beneath it. Both descriptions agree on the outcome. They differ on which part of the process deserves the most attention, and that detail is still debated among astrophysicists modeling stellar interiors. Radiation pressure plays its own quiet role in this swelling. Light itself carries a small outward push, and in a star this large, that push adds up. As the sun's luminosity, its total output of light and heat, climbs during this phase, radiation pressure grows too, helping shove the outer gases even farther from the core. Meanwhile, the sun's magnetic field, which today drives sunspots and solar flares, may weaken or reorganize as the internal structure changes, though exactly how it behaves during this transformation is not fully mapped out. If you stood on a nearby world, you would feel the light on your skin change slowly, growing warmer across centuries, long before anything looked dramatically different in the sky. There is also the slow loss of the sun's own mass to consider, carried outward on the solar wind, the constant stream of charged particles flowing from its surface. As the sun ages and swells, this wind may thicken, and some of the sun's mass drifts away into space rather than staying bound in gravity's grip. Losing mass weakens gravity's pull on the planets, which raises a quiet question that will return again and again in this story. Could a planet's orbit drift outward just enough, just in time, to escape being swallowed by the swelling star? The evidence is incomplete, and the outcome may depend on details we have not yet measured precisely, like exactly how much mass the sun sheds and exactly when. None of these forces act alone. Gravity, heat, pressure, light, and the solar wind all lean against each other in slow motion, across millions of years, reshaping a star that once seemed unchanging. If you had grown up beneath this sun, you would have called it steady, reliable, almost boring in its sameness. Yet, beneath that calm surface, forces have always been in motion, waiting for the fuel to run thin. The argument between gravity and pressure does not end quickly or quietly. It simply shifts its terms, and the sun begins the long, slow work of becoming something enormous. Picture the sun as it is right now. Shrink it down to the size of a basketball, and Earth becomes a peppercorn, drifting about 26 yards away. Mercury would sit just 8 feet from that basketball, close enough to feel the heat pouring off it. If you held that peppercorn in your palm at 26 yards, your skin would still feel warm from the small orange sphere across the yard. Now hold on to that image, because it is about to be wrong. When the sun becomes a red giant, that same basketball will not stay a basketball. It will swell until it fills the space of a sphere over 200 times wider than it is today. In our little scale model, the basketball would grow until it swallowed the spot where Mercury used to float. It would keep growing until it reached out past Venus and very nearly touched the peppercorn that is Earth. Numbers like this are hard to feel, so let's slow down and sit with just one of them. 200 times wider does not sound like much when you say it quickly, but size grows in 3 dimensions, not 1. A star 200 times wider than the Sun does not have 200 times the volume. It has roughly 8 million times the volume. Imagine a house expanding until it swallows an entire mountain range, and you begin to sense the shape of that number. If you could stand on a hillside and watch this happen across a human lifetime, you would notice nothing at all. The scale of it defeats the scale of us. Your body would age and pass on before the Sun's surface crept even a fraction of the distance toward Earth. This is a transformation measured in hundreds of millions of years, unfolding so slowly that no single lifetime, no single civilization even, could watch it happen from start to finish. That slowness is part of what makes the mystery so strange. It is a catastrophe with no dramatic moment, no single day anyone could point to and say, this is when it happened. Consider the Sun's mass for a moment too. Even as it swells to an unthinkable size, the material inside it does not multiply. The Sun will actually shed a portion of its mass. As this happens, a slow wind of matter drifting outward into space. Some researchers estimate the Sun could lose somewhere close to 1/3 of its current mass by the time it finishes its red giant swelling. That loss matters because a lighter Sun pulls less strongly on everything orbiting it. One idea is that this loosening grip might let planets drift a little farther out, buying them a small measure of safety. Another view suggests the drag of the Sun's outer atmosphere, once it grows large enough to touch a planet's orbit, would matter far more than any gentle loosening of gravity. Which effect wins, for which planet, is still an open question that depends on details scientists are still working out. Try one more comparison, because scale deserves more than one image to land. If Earth's entire 4.5 billion year history so far were compressed into a single day, the Sun's red giant transformation would not even begin until well past midnight, in the final sliver of time before a new day starts. We are, right now, living in the Sun's stable middle years, its long and quiet afternoon. The swelling into a red giant is still comfortably in the Sun's future evening, an event so distant that measuring it in years barely helps. Billions of years is not a number your mind can hold on to. So instead, hold on to this. Everything you have ever known, every sunrise, every human life ever lived, fits inside a stretch of time far shorter than what remains before this begins. If you floated somewhere out past Jupiter and watched this unfold across those hundreds of millions of years, your body would feel almost nothing change at first, only a light growing very, very slowly warmer against your skin. The temperature at the Sun's own surface would actually drop as it expands, cooling to a deep orange red, even as the sheer size of that glowing surface makes it burn brighter overall in the sky. A star can grow cooler and more dangerous to its worlds at the same time, simply by becoming enormous. That paradox alone is worth sitting with in the dark. Scale, in the end, is the real subject of tonight's wandering. The strange fact that something can be both slower than a human life can measure and larger than a human mind can comfortably picture, closing in around its own children, so gradually that no one and nothing will ever feel the exact moment it happens. If you stood on Mercury today you would feel a world already scorched. The ground beneath your boots would be grey and cratered, cracked by heat during the day and frozen hard at night. This is the planet closest to the Sun, and even now, billions of years before any red giant swelling begins, it carries the marks of a long, hard relationship with its star. Mercury has no real atmosphere to soften anything. There is no wind to smooth the dust, no clouds to scatter the light. The Sun above would look nearly 3 times larger than it does from Earth, and its glare would fall directly onto rock, with nothing standing between them. If you looked down at your own hands in that light, you would see them lit with a harsh, flat brightness. No haze, no softness, just raw sunlight striking raw stone. Some craters near Mercury's poles hold something surprising. Deep inside their shadowed floors, permanently out of direct sunlight, there is water ice. It has likely sat there for a very long time, protected by darkness, even on the hottest planet close to the Sun. It is a strange detail to hold in mind. Ice quietly waiting in the dark on a world that spends most of its time baking. None of that will matter in the end. As the Sun ages and begins its slow swelling into a red giant, Mercury sits closest to the transformation and closest to the danger. Its orbit lies well within the distance the swollen Sun is expected to reach. Most models suggest that when the Sun expands, its outer layers will grow far past where Mercury circles now, meaning the planet will not simply feel more heat. It will be inside the star itself. Picture what that final approach might look like if there were anyone there to watch it. Over millions of years, the Sun would grow larger in the sky, slowly, patiently, the way a shadow lengthens as the afternoon wears on. The line between space and Sun would blur. What was once a small, brilliant disk would become a wall of light, stretching wider each passing age, swallowing more and more of the black sky around it, long before Mercury's rocky surface ever touched the Sun's outer gases. The heat alone would have finished the planet. Temperatures would climb far past anything its cratered face has ever known. If any ice still waited in those shadowed polar craters, it would boil away long before contact, released as vapor into a sky no longer dark. Here the open question begins. Some researchers think Mercury may not simply sit still and wait to be engulfed. As the Sun sheds mass in its red giant phase, its gravity weakens slightly, and planets tend to drift outward in response, like a dog whose leash grows longer. One idea holds that this outward drift might happen fast enough to save some worlds from being swallowed directly. Mercury, being smallest and most exposed to drag from the Sun's outer atmosphere and thickening stellar wind, is considered by most models the least likely to escape that fate. A competing view focuses on the drag itself. As the Sun's outer layers puff outward, that outer material is thin but wide, and a nearby planet moving through it would feel resistance, like a hand dragging through water. The drag could slowly steal orbital energy from Mercury, pulling it inward, even as the Sun's weakening gravity tries to let it drift out. Which effect wins? The outward push from lost mass or the inward pull from atmospheric drag is still being worked out through calculation and simulation, not direct observation. No one has watched a planet actually go through this. The evidence is built from physics and modeling, not memory. If you floated above Mercury during this final chapter, the silence would remain unbroken, even as everything changed. There would be no sound of the star arriving, no crack or roar as gases surrounded the planet. Heat does not announce itself with noise in the vacuum of space. You would simply watch the Sun's edge grow closer, month by month, year by year, until sky and star were no longer separate things. Whether Mercury is consumed slowly, its rock vaporizing into stellar gas, or destroyed instantly at the moment of contact, remains a detail scientists cannot yet fully resolve. What is agreed upon is simpler and quieter. Mercury will not outlive the Sun's expansion. It is the planet with the least room to run, the least distance between where it orbits now and where the story ends. Its fate feels almost like a foregone conclusion, and yet even foregone conclusions carry mysteries in their details. The timing, the manner, the exact shape of an ending still being calculated by careful hands, staring at numbers instead of skies. Picture yourself drifting above Venus, close enough to see its thick yellow clouds moving in slow, endless waves. Beneath those clouds hides a world already close to the edge of what heat can allow. Your body, if it could feel anything there today, would feel crushing pressure and furnace air. And this is only how Venus looks now, long before the Sun begins to swell. Venus is often called Earth's twin. It is close to Earth in size, and it sits just one planet closer to the Sun. But that small difference in distance has always made a large difference in heat. Even now, the surface of Venus is hot enough to melt lead. Scientists still debate exactly why Venus turned out this way, while Earth did not. One idea points to a runaway greenhouse effect, a process where trapped heat builds on itself until a planet's water boils away completely. If this idea is right, Venus may show us a preview of Earth's own far future, as the Sun ages and grows brighter. Long before it becomes a swollen red giant, its output of light and heat will slowly climb. Venus will feel this first. Whatever thin traces of activity remain in its atmosphere will likely fade further under the added heat. The deep clouds may thin. The surface, already dry and cracked, may grow only more hostile. If you stood there in that far future, your skin would feel heat rising like an invisible tide with nowhere to escape. The real ending, though, comes later, when the Sun begins its transformation into a red giant, a swollen, cooler, but far larger version of itself. At that stage, models suggest the Sun could grow enough to reach Venus's orbit entirely. If that happens, Venus would not fall slowly through empty space toward the Sun. It would already be inside it. The outer layers of the star, thin and glowing, would surround the planet like fog swallowing a hill. Some researchers describe this kind of ending as if the planet simply stops mattering. Deep inside a red giant's outer envelope, gas pressure is low, almost like a bright hot vacuum, but drag still exists. Venus would not explode or shatter suddenly. Instead, it would experience something more like erosion, its orbit slowly shrinking as it moves through the star's material. Over years, then decades, then centuries, it would spiral closer to the Sun's true core. If you tried to imagine standing on that surface during the process, you would feel gravity pulling your body one way, while an invisible wind pushed the ground itself, slow and relentless, in another. Not every scientist agrees on how completely Venus would be destroyed once inside the Sun's outer layers. One view holds that a rocky planet like Venus would gradually vaporize, its minerals turning to gas and mixing into the star's thin outer material. Another view suggests some dense metallic core material might survive longer, sinking rather than dissolving, at least for a while. Neither idea has been confirmed, because no telescope has ever watched a rocky planet die this way in real time. What we have instead are calculations, simulations, and comparisons to other dying stars, distant evidence offers hints rather than certainty. Astronomers have found stars whose chemical makeup looks unusual, holding traces of elements normally found on planets, not inside stars. Some researchers wonder if this is a sign of a planet's remains, pulled apart and swallowed. Other astronomers caution that stellar chemistry can be strange for many reasons unrelated to planet consumption. The evidence remains suggestive, not conclusive. Somewhere in the galaxy, a version of Venus's ending may already have happened to another world, silently, unnoticed, long before we ever pointed a telescope in its direction. For Venus itself, the outcome still depends on details we have not fully worked out. Some models place its final engulfment at a point when the Sun has grown just large enough to reach it. Other models suggest the Sun's outer edge may fall slightly short of Venus's orbit, leaving it scorched, but technically outside the star. The uncertainty comes from how much mass the Sun loses as it ages, since a lighter Sun holds its planets with a gentler grip, letting orbits drift outward slightly over time. If you could watch from a great distance, you might see Venus either vanish quietly into the glow or hang for a while at the very edge of it, blistered and airless, circling a star far larger than the one it once knew. Either way, no clear line marks the moment of ending. There is no flash, no sudden collapse, only a slow closing of distance, a planet folding into the same star that once warmed it gently from far away. If you stood on Earth's surface, 5 billion years from now, you would feel the ground still solid beneath your feet. That is the strange part of this story. Earth's fate is not settled the way Mercury's fate is settled, or Venus's. It sits at the edge of a question that scientists still argue over, gently, the way you might argue over a horizon that keeps moving as you walk toward it. Here is what we do know. As the Sun swells into a red giant, it will lose mass through a slow outward breath of gas, called a stellar wind. Losing mass means losing gravity, and losing gravity means its grip on the planets loosens just a little. Some models suggest this loosening could let Earth drift outward, gaining distance from the Sun, even as the Sun itself grows to fill the space where Earth used to be. It sounds almost hopeful, a planet nudged to safety by the same star, trying to consume it. But other models tell a different story. They suggest the drag from the Sun's outer atmosphere and the pull of tides between a swollen star and a nearby world could work against that outward drift. Tides, raised by close, bloated Sun, could slow Earth's orbit rather than widen it. A slower orbit means a tighter spiral. The two effects, mass loss pushing planets out and tidal drag pulling them in, seem to compete with each other, and no one is fully certain which one wins for a planet at Earth's exact distance. That uncertainty is not a small detail. It is the entire question of whether Earth survives as a physical object at all. Picture the timeline the way you might picture the seasons turning, but stretched across billions of years instead of months. The Sun brightens slowly now, a fraction of a percent every 100 million years, the kind of change too slow for any single lifetime to notice. Long before any red giant swelling begins, that gentle brightening alone will end life on Earth. Oceans will begin to evaporate, rock will begin to break down under heat in ways it does not now. This happens perhaps 1 billion years from now, long before the Sun ever balloons outward. Whatever answer the red giant phase holds for Earth's rocky body, the living world, the blue and green world you might picture right now, will already be gone. You would not feel that ending as a single moment. There is no eruption, no crack in the sky. It would arrive the way a tide arrives, in cycles, in small steps that repeat and repeat until nothing is the same as it was. Warmer summers, drier decades. Ice sheets shrinking a little more each cycle, instead of returning to their old size across. Enough of those cycles, a living planet becomes a bare one, still turning, still orbiting, just silent now. Then, further out in time, the second phase begins. The sun exhausts the hydrogen fuel in its core, swells into the red giant we have been describing, and this is when the mass loss and tidal drag question finally gets tested against the real body of the Earth. If the outward drift wins, Earth may end up circling far outside the sun's new bloated surface, a scorched, sterile ball of rock, orbiting in permanent close range to a star grown enormous in its sky. If the tidal drag wins, Earth may instead be drawn inward, joining Mercury and Venus in whatever the sun's outer layers do, to a world that crosses inside them. Some researchers have looked for answers in other star systems, watching red giants elsewhere in the galaxy, for planets caught mid-transit through this very process, air. A few candidate cases exist. Stars that show chemical signs consistent with having swallowed a planet recently, cosmically speaking. These cases are suggestive rather than certain. They give us hints about how the physics tends to resolve, without telling us how it resolves for a planet at exactly 1 astronomical unit, the average distance between Earth and the Sun today. If you imagine standing on that future Earth, whichever version turns out to be true, you would look up at a sun no longer as it is now. It would fill more of the sky, its edges softer, its light more orange than yellow. The rhythm of your planet's whole existence, spin and orbit and season, would already have slowed and simplified into a single long fading breath. Whether that breath ends with Earth intact and distant, or drawn into the fire that made it, remains one of the genuinely open questions in the story of our solar system's end. For now, the cycles continue, day into night, orbit into year, the sun rising quietly the same way it has for 4.5 billion mornings. Picture yourself standing on a quiet hillside long before any of this begins, watching the sky still friendly to the eye. This is the part of the story where we look sideways, not just ahead. Earth will drift near the edge of the fire, as we heard. But Earth has neighbors, and neighbors change everything in a slow gravitational dance no one fully understands yet. Think of the habitable zone, that narrow band of orbits where a planet stays warm enough for liquid water, but not so hot that it boils away. Right now, Earth sits near the center of that band. As the sun swells into a red giant, the whole zone will drift outward, sliding past Earth like a tide moving up a beach. Mars might find itself, for a while, standing where Earth once stood, wrapped in warmth it has never known before. If you stood on that future Martian ground, the frozen dust under your boots would soften. Ice buried for billions of years would begin to sigh into vapor. The thin, cold air that Mars wears today would thicken, and for some stretch of time, water might pool where it has not pooled since the planet was young. Some researchers wonder if this brief window could ever support anything alive, even something as simple as microbes stirred awake by unexpected heat. But the timing matters more than the warmth itself. The sun's red giant phase does not creep in gently and then hold steady. It builds slowly across hundreds of millions of years, then accelerates as the star swells to nearly 200 times its current width. A world drifting into comfort today may find its comfort erased within a few million years. A blink in cosmic terms, but an eternity too short for evolution to answer the invitation. If you imagine life taking hold on such a world, you would be imagining a guest arriving just before the house catches fire. This is where the competing idea comes in. Some scientists lean toward a cautious no, arguing that any newly warmed world would lack the deep chemical history that living things seem to need, the slow accumulation of organic molecules, the stable seas, the patient centuries required for anything resembling biology to organize itself. A planet, given only a short thaw, they argue, is not the same as a planet given a childhood. Warmth alone may not be enough. The debate remains open, resting on how quickly life can begin when the ingredients and the moment finally align. There is also the question of moons, Jupiter's icy moons, sitting so far from the sun today that their surfaces stay locked in frozen silence, may receive their own brief invitation as the habitable zone sweeps outward. If you could stand on the cracked ice of a moon like that in some future era, you might feel the ground groan beneath you as heat reaches layers that have never softened before. Subsurface oceans, hidden for billions of years beneath miles of ice, could stir for a while. Whether such stirring could ever support anything alive is one of the more haunting unanswered questions in this whole slow unfolding story. And then there is the shadow side of neighborly warmth, radiation. A red giant does not simply glow gently longer and brighter. Its outer layers, stretched thin and unstable, blow off streams of charged particles far more forceful than anything the young sun ever produced. If you stood on a world newly nudged into the habitable zone, you would feel that light differently than sunlight feels today. Harsher, more restless, carrying an intensity that could scour a thin atmosphere away. Before life ever got the chance to notice its own warmth, some theorists picture the whole neighborhood shifting like dancers exchanging places at a slow, cosmic pace, each world briefly warmed and then abandoned as the sun's fire moves outward through the solar system. Others see it less as an invitation and more as an eviction, since every world touched by that expanding warmth is also a world drawing closer to a star that will eventually reach much of that space directly. Both views agree on one point. Nothing that borders a dying sun stays untouched. Warmth arrives everywhere, eventually, whether as a brief gift or as a final erasure. If you tried to imagine watching this from a great distance, you would see it as a slow wave of light, moving planet to planet, moon to moon, touching each world, only long enough to ask a question it may never get answered. No one knows whether life could rise fast enough to meet that wave, or whether the sun's warming reach is simply too brief, too fierce, and too late for anything but curiosity to survive it. Long before any planet touches the swollen sun, water disappears. If you stood on a rocky world at that late hour, you would feel the air grow thin and dry, as if someone had quietly let the moisture out of the sky. Oceans do not wait for fire to reach them. They leave early, boiled away by heat that arrives long before the sun's surface does. This is one of the sun's slow, hidden weapons. As it brightens, even gently, the extra warmth builds up in a planet's air and water. A wet world does not need direct contact with the sun to lose its oceans. It only needs a few degrees of patience. Climate scientists who study Earth's own far future describe something they call a runaway greenhouse, a point where rising heat causes more water to evaporate, and that water vapor traps even more heat, until the whole ocean lifts into the sky and never comes back down as rain. Your skin would feel this shift as a kind of creeping dryness, decades before anyone called it dangerous. Rivers would thin first, then lakes. The largest oceans would hold on longest, retreating instead of vanishing outright. But the ending would look the same everywhere in time. Water vapor rises into the upper air, where sunlight breaks it apart into hydrogen and oxygen. The light hydrogen drifts up and escapes into space, atom by atom, and once it is gone, it does not return. A planet cannot rebuild an ocean it has already breathed away. Some researchers believe Earth itself may lose its oceans this way, well before the sun becomes a red giant, perhaps in about 1 billion years, driven by nothing more dramatic than a star slowly turning up its own brightness as it ages. Other models place that boiling point later, closer to 2 billion years out, depending on how clouds and ice respond to the extra heat. The uncertainty is real. Small assumptions about cloud behavior shift the estimated timeline by hundreds of millions of years, and no one alive today can say which model will prove closer to correct. Venus offers a haunting preview of what this looks like when it finishes. Some scientists think Venus once held oceans of its own, in a warmer, wetter youth close to the young sun. If that is true, those oceans were lost long ago, likely through this same runaway process, leaving behind the scorched, waterless world we see today, wrapped in thick, sulphurous cloud instead of blue sky. Venus did not need the sun to expand into a giant to lose its water. Ordinary sunlight, sustained over a long enough stretch of time, was apparently sufficient. That is part of what makes this early phase of the sun's story so quiet and unsettling. The oceans do not need drama to disappear. They only need time and warmth working together without pause. If a planet still had inhabitants during this slow drying, they would notice the change first in the color of their sky and in the strange new absence of storms. Since storms need water to form, coastlines would recede year after year, exposing seafloor that had not seen open air in billions of years. Fish and reefs, if they still existed, would die long before any human observer needed to worry about the sun's outer edge reaching their solar system. The order of destruction is worth sitting with. Oceans first, at gentle heat. Atmospheres next, as heavier gases slowly follow the hydrogen upward and away. The solid ground endures the longest, bare and cracked, waiting for a sun that has not yet arrived to finish what its light already started. Astronomers studying other solar systems have found indirect evidence for this same pattern elsewhere, in the chemical signatures of atmospheres around aging stars. The evidence is suggestive rather than certain, gathered from light passing through distant atmospheres millions of light years too far to see directly. Still, the pattern holds in more than one place we have looked, which lends the idea some quiet support. You would not hear an alarm on the day the last ocean finished disappearing. There would be no explosion, no sudden storm to mark the moment, just a dry wind moving over ground that used to be a seafloor, under a sun that looked almost the same as it always had. The boiling away of a world's water may be the loneliest ending in this whole long story, because it finishes so early and so quietly that the true fire arriving later almost seems redundant by comparison. Picture yourself standing on a rise of dry ground, looking up at a sky that no longer holds any blue in it at all. Your body would feel the heat first, pressing against your skin like a hand held too close to a lamp. But your eyes would notice the color, or rather, the absence of it. The blue we know, the blue that fills our sky on any ordinary afternoon, comes from tiny air molecules scattering short blue wavelengths of light, more than they scatter red or yellow. that scattering only works one way, with a small, hot, concentrated point of light, like our sun sitting far away in a cool, thin sky. As the sun swells into a red giant, both halves of that equation change at once. The light itself turns redder. A red giant glows with a cooler surface than the sun does now, somewhere around 3000 degrees Celsius, instead of the sun's present 5500. Cooler stars send out less blue light to begin with, so there is simply less of it for the sky to scatter in the first place. At the same time, if a planet's atmosphere survives that long, it would likely be thickening and warming under the swollen star's glare, changing how any leftover light bends and bounces above the ground. Some researchers who model these late atmospheres suggest the sky could shift toward a deep orange, or a color closer to old brass, or something with no name yet, because no one has ever stood beneath it. There is a quieter detail hiding inside that color change, one that rarely makes it into the bigger, more dramatic descriptions of a star's death. The line between day and night would stop looking like the crisp edge we know on Earth today. Sunset borrows its drama from a small bright disk slipping behind the horizon, while blue light drains from the sky in minutes, under a red giant that fills a much larger portion of the sky. Sunset might stretch on for hours, the light fading the way a dimmer switch turns slowly rather than a lamp switching off. If you stood there long enough, you might lose the ordinary sense of where daytime ends and evening begins. Scientists, studying red giants elsewhere in the galaxy, have started to notice something else worth sitting with quietly. A handful of aging stars show odd fluctuations in brightness and puzzling chemical fingerprints in their outer layers, patterns some astronomers think could be leftover signs of a planet being pulled apart and swallowed inside the star's expanding body. The evidence is far from settled. Other explanations, like ordinary pulsations of the star's own gas or activity deep in its convecting layers, could produce similar signals without any planet involved at all. No one has caught a world in the act of disappearing, only these faint afterglows that might or might not be a memory of one. There is a texture to red giant light too, not just a color, because these stars have loosely held outer layers. Their surfaces churn with enormous convection cells, patches of rising and falling gas, so large that a single one could dwarf the distance between Earth and its moon. From the ground of a nearby world, this would not look like the calm, steady disk we see from our sun now. It would look mottled, restless, almost alive, with slow, bright welts moving across its face over the course of days. Your eyes, if you had time to adjust to such a sky, would start to notice how uneven that light really is, how it never holds perfectly still. Astronomers still debate how much surface detail like this would even be visible through the murk of a warming, thickening atmosphere. Some models suggest any leftover air on a surviving planet would grow hazy and diffuse the view, softening those bright welts into a general orange glow. Others argue a thin, dry atmosphere might let more detail through, at least for a while, before the heat finally strips it away. Nobody has an atmosphere sample from a world in this exact stage to check against, so the guess remains a guess, built from models rather than direct sight. What stays with you more than any single number about temperature or wavelength is the strangeness of a familiar sky slowly becoming unfamiliar, blue fading, sunsets stretching past all memory of an ordinary evening, a star's face developing its own moving weather, visible without a telescope. If you were there to see it, your breath would slow just from watching it, the way anyone slows down in front of something too large and too gradual to rush. picture the moon, hanging quietly beside a dying Earth. Your body would feel almost nothing different from this distance at first. The moon has followed Earth for over 4 billion years, and it will follow Earth through the sun's final swelling too, a small grey witness with no air to carry sound and no water to boil away. Learning what would happen to the moon took a strange path through history. Early astronomers were not thinking about endings at all. In the 1830s and 1840s, scientists like John Herschel and others catalogued nebulae through their telescopes, faint smudges of light scattered across the dark. Some of these smudges were shaped like rings or shells. Nobody yet understood that these shapes were the ghostly outer layers of stars that had already died, the very fate awaiting our own sun. The word used for these objects, planetary nebula, was actually a mistake. Through small telescopes, these glowing shells looked round and fuzzy, similar to how planets like Uranus appeared. The name stuck even after astronomers realized these had nothing to do with planets at all. They were the discarded skins of dying stars. It took much longer for anyone to ask what happens to the moons and planets already orbiting a star as it sheds itself this way. The mathematics of orbital decay, how a moon or planet slowly spirals inward or drifts outward as its star loses mass, was worked out gradually through the 20th century. Astronomers realized something important and easy to miss. When a star loses mass, its gravity weakens, and anything orbiting it tends to drift slightly outward, not inward, at least in the simplest calculations. This seems hopeful. A shrinking gravitational pull might let the moon, and perhaps Earth too, ease away from the sun as it becomes a red giant, buying a little more distance, a little more time. But this simple picture met a competing complication. As the sun expands into a red giant, its outer atmosphere puffs outward far beyond its current edge, and this thin gas creates drag on anything orbiting inside it. Drag slows an orbit down, and a slower orbit falls inward rather than escaping outward. So too, forces work against each other. Mass loss tends to push planets and moons away. Atmospheric drag tends to pull them back in. Which force wins depends on timing, on exact distances, on details that remain difficult to pin down, even now. This tension is at the center of the open question about which worlds truly escape a dying sun, and which do not. The moon complicates the picture further, because it is tied so closely to Earth. If Earth drifts outward as the sun loses mass, the moon likely goes with it, locked in its slow monthly circuit around a planet that is itself circling further from the flames. If Earth instead spirals inward from drag through the sun's outer layers, the moon would share that fate too, dragged along beside its only companion. Some researchers have modeled scenarios where the moon might be lost separately from Earth, pulled loose by the changing balance of gravity as the sun swells and weakens at different rates. This remains speculative. The interactions are complicated enough that confident predictions are hard to make, and different models built by different teams have produced different outcomes for the same rough scenario. Observational evidence has come from an unexpected place, not from watching our own solar system, which cannot show its future yet, but from studying other stars further along the same path. Astronomers, using instruments like the Kepler and TESS space telescopes, have found signs of planets that appear to be spiraling into their aging stars right now, caught mid-collapse in systems light years away. One well-known case involves a planet whose orbit appears to be shrinking year by year, consistent with the drag scientists predicted decades earlier from theory alone. These distant examples give some support to the idea that inward spiraling is common, though whether every planet meets this fate, or only some remains unresolved. If you stood on the moon during this slow unfolding, you would feel no wind and hear no warning, because the moon has no atmosphere to carry any sound at all. You would simply watch the sun grow larger in a black sky, day after day, year after year, its edges softening from a bright disk into something vast and reddened. The moon offers no shelter and no explanation. It only continues, as it always has, holding its position beside Earth, while the question of where that position finally leads remains open, unfinished, and quietly unresolved. If you stood on Mars while the sun swelled into its red giant phase, you would notice something strange about hope itself. Mars sits farther out than Earth, colder, quieter, its red dust untouched by oceans for ages. That distance might seem like safety. The question of whether it truly is safety remains open, and the answer is stranger than a simple yes or no. Mars orbits about 1.5 times farther from the Sun than Earth does. When the Sun expands into a red giant, some models suggest its outer edge could reach close to where Earth orbits now, maybe even past it. Mars would sit just beyond the reach of the swollen star's surface, close to the new edge of destruction, but perhaps not inside it. That word, perhaps, matters. Nothing about this distance is settled. The heat alone would transform Mars long before the Sun's surface came anywhere near it. The red giant Sun would blaze thousands of times brighter than it does now. Mars's thin atmosphere, already fragile, would offer little shelter. Any ice, still hiding in its polar caps, or buried underground, would turn to vapor and drift away into space. The rust-colored plains would bake under a swollen orange sun that fills a huge stretch of the sky. If you stood there, your body would feel a heat with no relief, a light too bright to look toward, and a silence broken only by wind moving fine dust across ancient craters. Some researchers wonder whether Mars might briefly become almost pleasant before that happens. As the sun brightens over billions of years, the habitable zone, the region warm enough for liquid water but not too hot, will drift outward. Mars sits in the sun's future path toward warmth. There is a real possibility that ice on Mars will melt long before Mercury and Venus are swallowed, giving Mars a strange, brief window as a warmer, wetter world. That window would not last. As the sun continues to grow, that warmth would tip quickly into something closer to ruin. Whether Mars survives the red giant phase itself depends on details that remain genuinely uncertain. The sun will lose a significant fraction of its mass as it swells, blown outward, a stellar wind, a stream of particles escaping the star's grip. Less mass means less gravity holding the planets in their orbits. Some models suggest this loss could let Mars, and even Earth, drift outward as the sun's pull weakens, like a leash growing slack. This drifting might carry Mars far enough away to avoid engulfment even as the sun's surface pushes outward to meet it. Other models suggest the outward push of the growing sun could still outpace the outward drift of the planet, closing the gap instead of widening it. No one can say for certain which force wins. There is another layer of surprise tucked inside this question. Even if Mars escapes being swallowed outright, it would not escape unchanged. Radiation levels near a red giant climb far beyond anything the young solar system knew. Any thin remaining atmosphere on Mars, if it has not already been stripped away, would erode further under that radiation. The rocky surface, already barren, would become sterile in a deeper sense, cooked by ultraviolet light and stellar wind with no magnetic shield strong enough to block it. Your skin, if you could feel anything there at all, would register warmth long before your eyes adjusted to the strange, swollen light filling half the sky. Some scientists have looked to other star systems for clues about Mars's odds. Telescopes have found evidence of planets that appear to be spiraling into their aging stars right now, caught mid-collapse in systems light years away. Other observations hint at planets that survived a star's red giant phase, orbiting white dwarfs, the small, dense embers left behind after a star sheds its outer layers. Both outcomes appear to be real possibilities across the galaxy. Which one describes Mars's future is still an open question, one that depends on details of the Sun's mass loss that current models cannot fully pin down. What makes Mars a genuine surprise in this story is not a dramatic escape or a certain doom. It is the ambiguity itself. Sitting quietly at the edge of calculation, Mars might glow briefly as a warmer world before growing hostile. It might drift to safety only to bake under radiation, with no atmosphere left to protect it. It might be swallowed after all, if the Sun's expansion outpaces its own weakening pull. If you drifted above its dust plains during that far future era, you would feel the heat rise slowly, day by day, with no single moment marking survival or loss. Only a long, uncertain unfolding written across a red and darkening sky. Picture yourself drifting past the orbit of Mars, out where the light grows thin and cold. Out here, the gas giants wait in their slow, wide circles. Jupiter, Saturn, Uranus, Neptune. They seem far enough from any danger, but even they will feel the sun change in ways both gentle and strange. Right now, sunlight takes about 40 minutes to reach Jupiter. Your body, if you stood on one of its moons, would feel a sun that looks small and pale, a bright coin in a dark sky. When the sun swells into a red giant, that coin will grow. It will not swallow Jupiter, most likely, but it will fill more of the sky, and it will pour out far more heat than these cold worlds have ever known. The sun's total light output will rise sharply during the red giant phase, perhaps thousands of times brighter than it is today. That energy travels outward and touches everything in the solar system, not just the inner planets. Jupiter's icy moons, bodies that have spent billions of years locked in deep freeze, may finally feel warmth reach their surfaces. Some researchers wonder if this could briefly wake liquid water beneath their icy shells. Others think the warming will be too slow or too late, arriving only as the sun is already losing mass and fading toward its final collapse. The timing of warmth and the timing of decline may not line up kindly for anything that might have used it. There is a strange harmony in this. The same swelling star that threatens to consume Mercury and Venus, that will scorch Earth into a sterile stone, might also thaw ice that has never seen liquid form. Endings and small beginnings tangle together in the same stretch of time. Nothing here is guaranteed, but the idea that the same event could destroy some worlds while briefly softening others feels worth sitting with, quietly, in the dark. The gas giants themselves are built differently than Earth or Mars. They have no solid surface to scorch. Jupiter is mostly hydrogen and helium, layer upon layer of gas, thickening into liquid, then into something stranger, deep in its interior. A dying sun cannot burn what has no crust. Instead, the danger for these worlds comes from something quieter: gravity and the slow redrawing of orbits. As the sun loses mass, in its red giant phase, blowing material outward in a stellar wind, its gravitational grip on the whole system weakens. A lighter sun holds its planets more loosely. Orbits that were stable for billions of years may begin to widen, or shift, or wobble in ways that are difficult to predict precisely. Some models suggest Jupiter's orbit could drift outward as the sun sheds mass, moving further from danger rather than closer to it. Other models suggest the changes could destabilize the delicate balance between the gas giants, nudging them into new gravitational relationships with each other. The exact outcome depends on details still argued over by astronomers today. How fast the sun loses mass, how evenly, and how the giant planets respond to a universe that no longer pulls on them quite the same way. If you stood on Europa during this era, ice under your boots, you would feel the ground tremble faintly, not from heat, but from strain as gravity itself renegotiates its terms. This is a solar system reshaping itself from the inside out, not with one great event, but with a long, slow drift that connects the fate of the smallest icy moon to the swelling of the star at the center of everything. It is one system, breathing as a whole, even as parts of it change on wildly different timescales. We know of dying stars elsewhere that show hints of surviving planets, gas giants still orbiting where they once did, changed but not destroyed. But confirming exactly what happens to distant Jupiters and Saturns during a star's red giant phase remains difficult. The light of a swollen star drowns out the faint signals of anything still circling it, so astronomers piece together theory from scattered clues, shifts in starlight, debris disks, the occasional planet caught mid-transit through a dying star's outer layers. Your own solar system, if you could watch it end from a great distance, might show this same quiet complexity. Inner worlds gone, outer worlds bent into new paths, some closer to warmth, some pushed further from where they began. No fire reaches the gas giants directly. But nothing in this system moves alone. Every planet answers in some way to the slow unraveling of the star that made them possible. Picture yourself drifting near Jupiter, far out where the sunlight is thin and cold. If you rested there now, your skin would feel nothing but the deep chill of space, and the sun would look like a bright coin, not a fire. But billions of years from now, that same coin will swell into something enormous, and this quiet region of ice and rock may become the last place in the solar system that changes for the better before it changes for good. Jupiter itself will not be swallowed, even as the sun expands into a red giant, a star that has used up its hydrogen fuel and ballooned outward. Jupiter sits too far away for the swollen surface to reach it directly. But distance from the flames does not mean distance from their heat. As the sun grows brighter and larger, it will pour far more warmth into the outer solar system than it does today. Regions that have been frozen since the solar system formed may, for a time, feel something like a thaw. This is where Jupiter's moons enter the story. Europa, with its cracked shell of ice hiding a dark ocean underneath, already sits at the edge of curiosity for scientists wondering about life beyond Earth. Ganymede and Calisut, too, carry their own buried oceans, sealed under crusts of frozen water. If you stood on Europa's surface today, your body would freeze in moments, the cold so complete it would stop you before you took a second breath. But in the sun's red giant phase, some researchers wonder whether the increased heat could soften those icy shells, at least for a while, turning frozen worlds into something briefly more temperate. It is a strange kind of second chance, and it comes with real uncertainty. One idea: is that as the sun's radiation increases, the frost lines, the distances from the sun where ice can stay solid, will shift outward. Regions that once were too cold for liquid water might, for some window of time, warm just enough to let ice become slush, or even open water at the surface of a moon like Europa. If that happened, and if any dormant biology was sleeping in those buried oceans, it might briefly stir under new warmth arriving from a star that is otherwise destroying its inner worlds. But this vision has competing shadows. Life in Europa's ocean, if it exists at all, is not confirmed, and it may depend on this hidden ocean staying dark, cold, and chemically stable rather than being disturbed by outside heat. A sudden warming might not awaken anything. It might instead break apart the delicate balance that lets simple organisms survive in isolation for so long, if they were ever there to begin with. The truth remains completely unknown, and it may stay that way long after the sun has already changed shape. There is also the matter of time. The sun's transformation into a red giant unfolds over hundreds of thousands, even millions of years, not overnight. Any warming of Jupiter's moons would happen just as gradually, more like a season stretched to unimaginable length than a sudden event. If you tried to notice the ice melting while standing on Europa's frozen crust, you would feel nothing sudden at all, just the same patient cold, decade after decade, century after century, only slowly loosening its grip. And even this window of warmth would not last, as the sun eventually sheds its outer layers entirely, collapsing down into a smaller, dimmer remnant. The light and heat reaching Jupiter's moons will fade again. Whatever brief liquid water existed, if it existed at all, would refreeze into silence. The moons would return to their old, solid selves, but changed, holding whatever record their ice managed to preserve of the years the sun grew large and briefly generous with warmth. What makes this idea so quietly remarkable is the reversal it suggests. For most of the solar system's history, Jupiter's moons have been the cold outsiders, far from the sun's comfort. In the sun's dying phase, they might become, however briefly, the most hospitable rocky bodies left, while Mercury, Venus, and Earth suffer far worse fates closer in. Nothing about this is certain. It depends on ice thickness, radiation intensity, chemical composition, and questions about subsurface oceans that remain open even with today's spacecraft and telescopes. If you floated above Europa during that far future warming, your eyes might catch faint cracks glowing faintly under fractured ice, lit by a sun grown huge and red on the horizon. Whether anything moves beneath that light, no one can yet say. The moons keep their secrets the same way they always have, patient and frozen, waiting on a warmth that comes only once, and only for a while. Picture yourself drifting above Saturn, far enough out that the planet's curve fills half your view. Right now, in our present sky, sunlight reaches this place thin and pale, a small hard point of white light, 600 million miles from home, under a swollen sun. That light would change, and it would change everything the rings show you. Saturn's rings are made of countless pieces of ice, some as small as a snowflake, some as large as a house. Right now, they shine because they reflect the sun's light, cold and brilliant, throwing back a glow that makes Saturn one of the brightest sights in our sky. If you floated near them today, your body would feel a faint chill of sunlight, so diluted it carries almost no warmth at all. That thinness of light is part of what keeps the rings frozen, bright, and structured into their long, delicate bands. When the sun becomes a red giant, Its light will not simply grow stronger, its color will shift. Its output will swell by thousands of times. And even at Saturn's great distance, the ice in those rings would begin to feel it. Water ice reflects light well, but it also absorbs some. And over centuries, that absorbed warmth would add up. One idea is that the increased heat could slowly drive off the most exposed, most delicate ring particles, turning tight bands into looser, thinner scarves of ice and dust. A competing idea suggests the rings might last longer than expected, since Saturn's distance from the swollen Sunday may increase if the Sun sheds mass and loosens its gravitational grip on the outer planets. That possibility matters because a star does not just expand. It also, based on current models, loses a portion of its own mass as it sheds material into space through a strong outer wind. Weaker gravity from a star that has lost mass could let orbits drift slightly outward, giving worlds like Saturn a small measure of relief. Whether that drift would be enough to protect the rings from a sun many times brighter remains an open question, one that depends on details still not fully settled. If Saturn's orbit does hold roughly steady, and the rings survive the heat, the light itself would still look different than it does now. Sunlight passing through an expanded red giant atmosphere often takes on a deep orange or reddish hue, the last light of a dying furnace, rather than the crisp white light of a young star. Under that colored glow, the rings might shine faintly orange or copper instead of their familiar pale gold, an eerie beauty with no one left nearby to see it. You would notice, if you could stand on some icy moon nearby, how the shadows around you would take on that same warm, heavy color, as if the whole system had been dipped in dim firelight. There is also the question of the ring's structure itself, held in place by countless small gravitational tugs from Saturn's moons. If nearby moons shift their orbits due to changes in the Sun's pull, the delicate resonances that keep certain rings sharp and others empty could unravel. Some researchers wonder whether the rings might spread out into a broader, fainter disk long before the Sun fully expands, losing their crisp lines the way a drawing smudges with time. Others argue the rings are more robust than they appear, shaped by forces strong enough to outlast smaller disturbances. No spacecraft has watched a ring system pass through its star's red giant phase. So much of this remains guided by models rather than direct observation. Astronomers have found evidence of other planets and debris disks around aging stars, some showing signs of disruption, some strangely intact, offering only partial answers. Each distant system adds a small piece to the puzzle, but none of them matches our solar system closely enough to settle the question outright. What seems most likely, though still uncertain, is that Saturn's rings would not vanish in a single dramatic moment. They would fade slowly, ice sublimating grain by grain, particles drifting from their orbits over spans of time too long for any single observer to witness. If you floated there through those long centuries, you would feel the light around you grow warmer and redder, while the rings around you grew thinner and dimmer, a slow dimming rather than a sudden end. Whether they endure in some ghostly form or scatter into the space around a swollen dying star is still something no one can say for certain. For now, the rings still turn in the dark, gathering light from a sun that has not yet begun to change. Picture yourself drifting far out past Saturn, out where Uranus turns slowly on its tipped-over axis, and Neptune glows a deep, quiet blue. Out here, the sun is no longer a blazing disk. It is a bright point of light, sharp and small, no warmer to your skin than a porch light seen from far down a dark street. If you floated here, your body would feel almost nothing of the sun at all, just a faint pressure of light, thinner than a whisper. This far out, sound itself has a different story to tell. Space carries no air, so nothing here can truly rumble or hiss the way a thunderstorm does on Earth. But instruments can still listen in their own way. Spacecraft have flown through the solar wind, that thin stream of charged particles the sun exhales in every direction, and they have measured how it presses against magnetic fields. Scientists have taken those measurements and turned them into sound, so we can hear something like a hum or a low, breathy static, and it is one of the strangest sounds we have made from data collected in the dark. Out at Uranus and Neptune, that solar wind is stretched thin, spread across billions of miles until it is little more than a rumor of the sun. The hum grows fainter here, more like the last echo of a bell struck a long time ago. Some researchers wonder whether these outer worlds, so far from the sun's current warmth, might one day sit inside a very different kind of light. When the sun swells into a red giant, billions of years from now, it could grow large enough that its outer atmosphere brushes up against orbits that once belonged only to distant ice and silence. Neptune orbits about 30 times further from the sun than Earth does. Even a red giant, swollen to 200 times its current width, would likely fall short of reaching that far. Most models suggest Neptune and Uranus would stay outside the sun's new, bloated body, watching from a colder distance as the inner worlds vanish, one by one. But being outside the flames does not mean being untouched. As the sun sheds mass in slow, steady winds during this stage, gravity's grip on every planet loosens slightly, and orbits can drift outward in response. The exact math of how far and how fast remains an open question among astronomers who study these late stages of stellar life. If you stood somehow on an icy moon of Neptune during that era, the sun would look different than it does tonight. It would swell into a soft, reddish coal in the sky, brighter than before, but still small and far away, its warmth still too weak to melt the ice under your boots. You would feel the same cold, the same silence pressing in from every direction, while somewhere far behind you, worlds much closer to the sun would already be gone. The sound of that era, if we could ever hear it directly, might not roar or crackle the way we imagine an ending should. Some physicists picture it more like a slow, low groan, the sound of vast structures shifting under strain, closer to the deep creak of a glacier settling than an explosion. Solar wind researchers have already shown that the whisper of particles streaming past a planet can be converted into audible tones, and in theory, a much stronger stellar wind blowing off a dying sun would sing a louder, heavier version of that same song. No one has recorded it, because no one has lived to hear it. It exists only in models and imagination. Uranus and Neptune may end this story as quiet witnesses rather than casualties, cold worlds spinning at the edge of a much brighter, angrier sun, or their orbits may shift in ways we cannot yet predict, drawn slightly outward as the sun loses weight, or nudged by encounters with debris or other bodies disturbed by the chaos closer in. Both ideas remain live in the research, neither fully settled. What we do know is that distance is not the same as safety, and safety is not quite the same as staying still. If you lingered at Neptune's frozen edge through all of this, your body would feel the cold first, then the strange thinness of a solar wind grown into something almost like a voice. You would watch a reddened star breathe slowly outward, across the dark, and you would not be able to tell, just by looking, whether you were witnessing an ending or simply a very long, very quiet exhale. Picture yourself holding a scale, one pan filled with the sun as it is now, the other pan empty and waiting. That empty pan matters more than it seems. As the sun ages and swells, it will also quietly lose weight. And that single fact may decide which planets survive. Here is the strange part of the math. A star does not swell without cost as the sun burns through its hydrogen and grows into a red giant. It will also push huge amounts of its own material out into space on a slow stellar wind. Over billions of years, the sun will shed something like a third of its total mass before it finishes its expansion. You would not feel this happening if you stood nearby. It unfolds too slowly, a whisper spread across ages, not a single dramatic breath. Losing mass sounds like shrinking. In gravity's math, it works the other way. A planet orbits its star because gravity holds it in a curve, and gravity depends on mass. If the sun becomes lighter, its pull on each planet becomes weaker. A weaker pull lets a planet drift a little farther out, the same way a slower spin lets a skater's arms drift wider. Orbits are not fixed roads. They are balances, and if you loosen one side of a balance, the other side must move to answer it. This is where the numbers offer something like hope, and where the hope runs into limits. Astronomers who model these systems, building the sun's future in equations rather than in a telescope, find that this widening effect is real and measurable in their calculations. Earth's orbit should stretch outward as the sun sheds mass, drifting to a wider circle than the one we travel now. Some models suggest this drift could carry Earth beyond the sun's swollen outer edge entirely, even as that edge grows to nearly reach us. If you tracked both numbers side by side, the sun's radius climbing and Earth's orbit climbing with it, you would be watching two rising lines that may or may not cross. The trouble is that a second force pulls against the widening orbit, and it does not appear in the simple mass loss equation. It is called tidal drag, and it works like friction between the sun's puffed up outer atmosphere and any planet passing close enough to graze it, even before full engulfment. A planet moving through the thin outer haze of a red giant loses energy to that drag, the way a satellite loses altitude brushing the top of a thin atmosphere. Energy loss means the orbit shrinks, pulling the planet back inward, even as mass loss tries to push it outward. Two forces, opposite directions, and the final answer depends on which one wins the race, and by how much. For Mercury and Venus, the math offers little suspense. They orbit close enough that the widening effect cannot save them. The sun's swelling outpaces any gain from its slimming waistline. For Earth, the outcome sits closer to the middle of the scale, and this is exactly why researchers keep returning to the calculation instead of closing the book on it. Small changes in assumptions, how fast the sun loses mass, how strong the drag becomes, how the sun's outer layers behave as they thin, shift the answer from survival to engulfment and back again. You are looking, essentially, at a coin spinning very slowly, one that will not land for a few billion years yet. Some researchers who study the sun's late life think Earth ends up hovering just outside the stellar surface, spared from swallowing, but scorched into a lifeless coal by the heat pouring off something that close. Others, running the same physics with slightly different numbers, model an Earth pulled inward by drag before it ever gets the chance to enjoy the wider orbit that mass loss offered it. Both groups are using real equations tested against real stars observed elsewhere in the sky. Neither claims certainty, because the sun's own future behavior, especially the exact rate and rhythm of its mass loss, still contains enough unmeasured detail to keep the outcome open. There is a kind of beauty in a mystery that comes down to arithmetic rather than mysticism. No monster decides Earth's fate, no chance encounter, no violent event, only a quiet contest between a star growing lighter and a star growing larger, worked out over eons in the patient language of gravity and drag. If you sat somewhere above that future solar system, watching only the numbers scroll past, you would see two curves reaching toward each other across billions of years, and even then you still would not know, not for certain, which one arrives first. Picture yourself standing on a wide plain, watching a scale so fine that a breath could tip it. That is what a planet's orbit looks like, up close. In the mathematics that describe it, every world moves along a path shaped by gravity, mass, and speed, balanced so precisely that a small push in any direction changes everything. Right now, Earth's orbit feels steady and eternal. In the red, giant future, that steadiness becomes something far less certain. As the sun loses mass through its outer wind, its gravitational grip on the planets weakens. Less mass pulling on a planet means a wider, slower orbit, the same way a loosened leash lets a dog wander further. Some models suggest Earth's orbit could drift outward by 10% or more as the sun sheds its bulk. Your body, if it could stay on that widening path, would feel almost nothing of the shift, since the change unfolds over millions of years, not moments. But this outward drift competes with an opposite force, one that pulls in the other direction entirely. As the sun swells into its bloated red giant form, it releases a slow wind of gas, and Earth moves through the outer edges of that wind like a boat pushing through fog. The drag from that thin, resistant material saps a tiny bit of orbital energy with every pass. Over enough time, that steady drag could slowly pull Earth's widening orbit back inward again. Which force wins depends on details still being worked out. The rate of mass loss, the density of the stellar wind, the timing of each stage of the sun's expansion. All of these numbers carry real uncertainty. Some calculations show Earth slipping just outside the reach of the swollen sun, saved by inches on a cosmic scale. Other calculations, using only slightly different assumptions, show Earth pulled back into the fire after all. The two outcomes sit close enough together that no one can say with confidence which one is correct. This is the strange truth about orbital mechanics near a dying star. The equations are precise, built from Newton's laws and centuries of refinement. Yet the answer wobbles depending on inputs no one can measure exactly yet. If you imagine standing at the edge of that calculation, you would feel the strange discomfort of watching two futures diverge from a single, tiny difference in starting conditions. A model that assumes slightly faster mass loss saves the Earth. A model that assumes slightly slower mass loss does not. It helps to remember how fragile the current arrangement already is, long before any of this begins. Earth orbits the Sun at almost exactly the right distance for liquid water to exist on its surface, a few percent closer, and the oceans might boil away today. A few percent farther, and they might freeze solid. The atmosphere above your head, thin as a coat of varnish on a globe, holds in enough warmth to keep the planet livable, while staying thin enough not to smother it. None of this had to work out. It simply did, through billions of years of gradual settling, and it continues to hold only because nothing large enough has disturbed it yet. The red giant sun represents the first truly large disturbance in that long, quiet balance. Other planets face their own versions of this same uncertain math. Mars, farther out, may drift into a temporarily gentler zone, only to be pulled by the same competing forces that make Earth's fate unclear. Venus and Mercury, closer to the flames, face little uncertainty at all. Their proximity all but guarantees consumption, regardless of which mass loss model turns out to be correct. Some researchers wonder whether even small gravitational nudges from Jupiter, tugging on Earth across hundreds of millions of years, could tip the balance one way or another. Others focus on the Sun itself, arguing that its own internal changes during the red giant phase matter more than any outside influence. No consensus has formed, and the uncertainty is not a failure of the science. It reflects how sensitive these systems truly are, how much depends on values still being measured in stars far older than our own. If you sat quietly at the edge of this unresolved calculation, you would feel the particular hush that comes from watching a question balanced on a knife's edge. Not fear, just stillness, the kind that settles over anything too vast and too slow to rush. Earth's fate in the Sun's final act may come down to a difference too small for today's instruments to see clearly. For now, the orbit holds, steady beneath you, unaware of the swelling star still billions of years away. Picture yourself watching from a great distance, far enough that the Sun looks calm again, a soft orange coal instead of a swollen furnace. This is the Sun near the very end of its red giant life, when something quiet and strange begins. The outer layers, the ones that puffed up over millions of years, start to drift away entirely. Slowly, in long breaths of gas, the Sun begins to shed its own skin. This process is called mass loss through stellar winds, and it has been happening the whole time the Sun has been a red giant, just more gently. Now, near the end, the wind grows stronger. Streams of hydrogen and helium leave the star and spread outward, forming a thin, glowing shell around the shrinking core. If you floated at the edge of this shell, your body would feel almost no push at all, because the gas here is thinner than any hospital vacuum. But the light around you would still glow with a strange, unsteady color, shifting as the dying star breathes out its last, unstable layers. The open question here is not whether this happens. It happens to countless stars across the galaxy, and astronomers have watched it unfold around others in real time, capturing the same star at different distances in its life, and piecing together a kind of picture book of the end. The real mystery is what happens to anything left orbiting the star while all of this is going on. Any surviving planet, moon fragment, or scattered rubble from a broken world would suddenly find itself circling a star that is actively losing weight, and losing weight fast. One idea suggests that this rapid mass loss loosens the Sun's gravitational hold. As the central mass shrinks, the invisible leash holding a planet in orbit weakens too. Some scientists propose that outer worlds, ones that survive the earlier expansion, might drift into wider, looser orbits during this final shedding, almost like a slow, unplanned escape. If a moon or planet had made it this far, its orbit would loosen bit by bit, matching the pace of the star's own unraveling. But there is a competing possibility, and it complicates the picture. As the Sun sheds mass, it does not do so evenly. The wind can be lumpy, faster in some directions, slower in others. And some researchers wonder whether this unevenness could actually destabilize orbits rather than simply widen them. A world could be nudged outward smoothly, or it could be tugged into a wobbling, unpredictable path. tumbling closer to instability instead of drifting safely away. No one has watched this happen to a planet in real time, since it takes far longer than any human lifetime. So this remains an open and genuinely uncertain question, adding to the mystery. Astronomers have found hints of planets caught mid-transition around other dying stars, worlds that seem to be sitting inside these expanding shells of gas, their fate still unfolding. Some studies have picked up faint chemical signatures, suggesting a planet was swallowed recently, its material now mixed into the star's outer atmosphere. Other observations show possible planets orbiting just outside the shredded material, seemingly untouched, at least for now. These findings are still being debated, and the evidence remains incomplete, but each new discovery adds another piece to the puzzle of what our own solar system might look like in its final chapter. There is also the question of timing. The shedding of the outer layers does not happen all at once. It can take tens of thousands of years, an instant by cosmic standards, but long enough that if a planet were still there, it would experience the shift as a slow, aching change rather than a sudden loss. If you had somehow survived until this point, standing on some frozen fragment of rock, you would watch the sky grow slowly thinner, the star's fierce edge fading into fine drifting threads of gas, its heat lessening not with a single moment of ending, but with the excruciating patience of the universe. Scientists still do not agree on exactly how much of the original solar system, if anything, might make it through this shedding intact. Some models suggest most of what remains close to the star will spiral inward long before this stage. Other models suggest the surviving material, freed by the star's dramatic weight loss, might scatter outward instead, wandering the space where planets once orbited in familiar, careful lines. Both pictures remain possible, and the true answer likely depends on details we have not yet measured with certainty. For now, this stage of a star's life sits at the edge of what we understand, a place where gravity, gas, and time interact in ways still being mapped out. If you drifted here, in this soft, dimming light, your body would feel the strange calm of an ending that refuses to hurry, a puzzle still being solved, one distant star at a time. Picture yourself floating far outside the old solar system, at a safe and quiet distance, watching something that took only a few thousand years to unfold, but changed everything. The swollen red giant has finished shedding itself. What is left glows in soft, expanding shells of gas, lit from within by a small, fierce ember. This is a planetary nebula. Despite the name, it has nothing to do with planets. Early astronomers, looking through weak telescopes, thought these glowing clouds looked like the pale disks of Uranus or Neptune, and the name stuck long after anyone knew better. Your eyes, if you could survive here, would take in colors that no simple word fully holds. Sheets of oxygen glow a cool teal green, clouds of hydrogen and nitrogen burn a deep rose red. The whole structure might spread into a ring, an hourglass, or a butterfly shape, its geometry still not fully explained by any single theory. The sun's outer layers, once so massive and slow, are now scattered across trillions of miles of space. This is the material we spoke of before, the skin the sun shed near the end of its red giant life. It carries carbon and oxygen forged deep in the star's furnace, elements it spent billions of years building. Your body, standing at a safe distance, would feel almost nothing physically, but you would be looking at raw material for future stars, future planets, maybe future life, drifting outward into the dark. At the center of this glowing shell sits the white dwarf, the exposed core of what used to be our sun. It is small, roughly the size Earth once was, but almost unbelievably dense. Its light is faint and cooling, no longer produced by fusion, but by leftover heat slowly leaking away. Some researchers estimate that a white dwarf like this will take longer than the current age of the universe to fully go dark. If you looked closely at that light, you would be looking at the final, patient version of the star that once warmed every planet in our system. The question that stays open is what became of those planets during this shedding. Mercury and Venus, we're fairly confident, were consumed long before this stage, swallowed whole during the red giant's expansion. Earth's fate remains less certain, caught somewhere between surviving as a scorched sterile husk and slowly spiraling inward to be lost as well. The outer planets, Jupiter, Saturn, Uranus, and Neptune, likely drifted outward as the Sun lost mass, their orbits loosening like a ball on a string, held by a weakening hand. Whether their moons kept their ice, whether their rings held together, whether any small rocky fragments survived the passage of the stellar wind, is still speculative. Some models suggest a handful of planets or planetary remnants could persist, drifting through the nebula on new, wider orbits. Other models suggest almost nothing. Large survives intact, ground down by radiation, tidal stress, and collisions with the escaping gas. Astronomers have found real evidence that this general picture happens elsewhere. They've observed planetary nebulae with clumps and asymmetries that some researchers believe were shaped by surviving planets, tugging gravitationally on the outflowing gas as it passed. Other researchers argue those same shapes come from stellar companions, magnetic fields, or rotation, no planet required. The debate remains genuinely open because we cannot yet see individual planets inside these clouds directly. We infer their presence, if they exist at all, from the shape the gas leaves behind. The nebula itself does not last. Within about 10 or 20,000 years, the shells expand and thin until they finally fade into the surrounding dark, mixing back into the wide, quiet material of the galaxy. If you tracked this same patch of space forward another few 100 million years, you would likely find nothing but the white dwarf, cooling in solitude, and diffuse gas dispersed so far it no longer resembles anything shaped or bright. What began as a single, ordinary star, with rocky worlds and icy moons circling patiently around it, ends as scattered atoms and one small dim ember. Whether any small fragment of what once was Earth persists, some drifting mineral remnant or slow orbiting cinder, is not something we can currently answer with confidence. It is one more open thread in a story that has many open threads. And still, from the ashes and gas of one ending comes material for new stars, new planets, and perhaps, somewhere far in the future, new questions asked by minds we cannot yet imagine. If you drifted here, at the quiet edge of this fading nebula, you would be looking at both an ending and a beginning, indistinguishable from each other in the dark. Picture a small dim ember hanging in the dark where a golden star used to burn. This is what waits at the end of the sun's long story. Astronomers call it a white dwarf, a dense leftover core about the size of Earth, holding almost half the sun's original mass. If you stood near it, your body would feel a pull far stronger than it does now, because all that mass is packed into a sphere no wider than the planet you once called home. The white dwarf has no fuel left to burn. It does not shine because it is making new light. It shines because it is still cooling, slowly from heat stored up over billions of years. Some researchers estimate that cooling process could stretch on for a span of time longer than the universe has existed so far. If you waited beside it, you would watch a fading coal that takes almost forever to go dark, its glow shifting from white to yellow to a deep, quiet red. Around this ember, the wreckage of a solar system may still drift. What is left of the outer planets, the ones that were far enough away to survive the red giant's reach, would circle a star that looks nothing like the sun you know. Gone is the warm yellow disk. In its place hangs a point of white light, small and sharp, casting a thin, cold glow across frozen worlds. One open question is whether any planets manage to stay in stable orbits around this new, lightweight star, since the sun will have shed roughly half its mass by then, loosening its grip on everything still circling it. Some models suggest that a planet like Jupiter, or moons like Europa and Titan, could end up orbiting farther out than before, nudged outward as the sun's gravity weakens. Other models suggest that gravitational chaos during the mass loss could fling smaller bodies away entirely, scattering them into the dark between stars. Nobody knows for certain which worlds, if any, will still be there when the dust finally settles. The math is complicated, and the timescales involved make direct observation of our own future impossible. We can only build simulations and watch other dying stars for clues. This is where the wider wonder comes in. The atoms that make up your body were not made in the sun. They were forged earlier, in older, larger stars that lived fast and died in supernova explosions long before our solar system formed. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it came from stars that expanded and burned and eventually scattered their contents into space. Those atoms drifted for ages before gravity gathered them into the cloud that became the sun and its planets. In a very real sense, you are made of stellar remains older than the world you stand on. One day, the sun will do something similar, though on a gentler scale. It will not explode. It lacks the mass for that kind of ending. Instead, it will puff away its outer layers in a soft, spreading cloud, leaving the white dwarf behind as a quiet core. Some of the atoms in that cloud, carbon and nitrogen and other light elements, will drift outward into the space between stars. Whether any of those atoms ever become part of a new star, a new planet, or something that might be called life, is entirely unknown. It is possible. It is also possible they simply drift unused for the rest of time. If you could stand at the very edge of that future scene, far enough away to be safe, you would see a small white point of light, surrounded by a faint ghostly shell of gas, slowly fading into the blackness around it. Your body would feel almost nothing there. No warmth, no pull beyond the whisper of old gravity. It would be quiet in a way that is hard to imagine now, lying here in the dark. And yet, that quiet scene would be built from the same kind of material that once made a warm yellow star, and once made the ground beneath your feet. The white dwarf is not really an ending. It is a slow, dim continuation, the sun's final shape after everything else has changed around it. Whether it holds on to any of its old family of planets, whether some of them escaped, whether some were swallowed long before this stage arrived, remains open. What is not open to question is the connection. You share your atoms with the stars, past and future. That thread runs all the way from ancient supernovae to this small ember of a star, and maybe further still, into worlds no one has imagined yet. If you could stand at the very edge of it all, at the end of everything we have wondered about tonight, you would find only quiet. No final flash, no dramatic curtain fall. Just a white dwarf, small and dim, cooling in the dark where a solar system used to be. Your body would feel weightless there, held by nothing, watched by no one. And that, in its own way, is the whole point of this story. We do not know exactly how our own solar system's ending will unfold. We know the broad shape of it. The sun will swell. Mercury and Venus will likely be swallowed whole. Earth's fate hangs somewhere between engulfment and survival as a scorched, airless ember. The outer worlds will drift into new light, new warmth, new uncertainty. But the fine details, the exact hour, the exact order, the exact mercy or lack of it shown to each small planet, remain unwritten. Some researchers lean one way, others lean another. The universe has not yet shown its hand. What we do have is evidence, scattered like faint light across other stars. We have seen the chemical fingerprints of worlds already consumed. We have seen red giants swollen with planets still spiraling in their final orbits. Each one is a kind of letter sent across the dark, telling us that this has happened before, elsewhere, to other suns and other worlds. Where it tells us exactly what will happen here is still an open question. The pattern is clear. The particulars are not. There is something comforting in that unfinished quality, if you let yourself feel it. If you are lying in the dark right now, wrapped in blankets, breathing slowly, you are not facing the sun's ending tonight. That ending is billions of years away, a distance so large it barely means anything to a human life. Your body is safe, your night is ordinary. The mystery we have followed through this episode is real, but it moves at the pace of stars, not the pace of clocks. Think, for a moment, of Earth as it is right now, still blue, still turning gently in the dark, still circled by its quiet moon. Somewhere on it, a person is falling asleep just like you, held by gravity that has not changed, warmed by a sun that has not yet begun to swell. The oceans are still liquid. The sky is still the pale blue we know, not yet washed white by a dying star's glare. This is the version of the solar system we get to live inside. It is fragile in the deep future, yes, but steady and whole for now. Some scientists imagine our descendants, if there are any left by then, finding ways to nudge Earth's orbit outward, buying a little more time under an expanding sun. Others think that is far too optimistic, that the forces at play are too large, too slow, too indifferent to human effort. Both ideas live comfortably in the space of things we cannot yet know. Neither one needs to be decided before you close your eyes tonight. What feels true across every section of this long, slow story is that the universe does not rush. Stars take billions of years to live and billions more to die. Even endings out there are gentle by our standards, stretched across time so vast that sudden barely applies. If you carry one feeling out of tonight's journey through red giants and doomed worlds and cooling white dwarfs, let it be that feeling of enormous, patient time. The universe is in no hurry, and neither do you need to be right now. Picture the whole solar system, one more time as it is tonight, not as it might be in the far future. The sun sits quietly at the center, small and steady. Earth turns in the dark, half in daylight, half in the kind of soft night you are in right now. Somewhere out past the ice giants, sunlight arrives so faint that it barely qualifies as day. And still it arrives, still it means something to whatever quiet worlds wait out there. All of it moves together, slowly, the way it has for billions of years, the way it will for billions more before anything like an ending begins. Let that image hold you as you drift off. A calm sun, a blue world, a dark, wide, patient universe outside your window, asking its questions softly, in no rush for answers. Some of those answers may come in your lifetime, many will not. Tonight, it is enough to have wondered, and to rest, subscribe for a brand new space topic every night. One tap and something incredible is waiting for you tomorrow. Sweet dreams.